That's one thing about doing online, I guess, and recording things. People can just not show up. I was wondering if there'd ever be a day where no one shows up, and I don't know what I do. Let's talk to myself. Was that? I said that could happen. So you guys doing fine? Rhiannon, do you have any questions, or how about you, Kiana? Are you doing all right? Do you need anything? Any questions?
All good. Thank you.
Okay. All right, so easy. It's very easy to know the names of the students when there's only 2 of them in the class. Well, there's 10. There's 10 in our class, but anyways, well, this is where I left off. Well, for the record, I actually made a mistake yesterday. I thought about that when I left class. I'm like, that was a dumb mistake. When I mentioned this function here, it's actually going to be x to the 9, not x to the 11th. That was a mistake. So it could be x to the 11th, because it could be a double, triple root, but it's the number of times it crosses the x-axis. So that was a dumb mistake. Sorry about that. I don't know if anyone noticed. But anyways, so back to chemistry, although math and chemistry are intimately involved. So where we left off, so we're talking about aqueous equilibria. So aqueous means water. So we're in water, and equilibria, so things in equilibrium. So, and equilibria, like in plural, you know, in Latin. So, and so now we're going to talk about, we mentioned this briefly last class, the solubility product constant. So almost everything that you have in water dissolves a little tiny bit. So calcite, calcium fluoride, for instance, is a sparingly soluble salt. So like sodium chloride salt, it's an extremely soluble salt. Like, I don't know, has anyone ever made brine before? Like when you brine a turkey or something like that? It's just amazing how much salt you can put into water. It's about 25% soluble. So you could probably put about a pint of that, you know, the salt that you get for the store for $1 in a gallon of water. It's amazing how much salt goes in the water. So salt, sodium chloride salt, is very soluble. And calcium fluoride, on the other hand, is not so soluble. It's very, very sparingly soluble, but it's a little tiny bit soluble. So if you put it into water, there is an equilibrium such that the solid slightly dissolves in the water. So you have an equilibrium where you form calcium and fluoride anions, calcium ions and fluoride anions. And don't forget there's a 2 here, so there's a 2 here. So just plain old stoichiometry. And then the equilibrium constant is going to be products over reactants, but the reactant is a solid, and solids are not included in equilibrium expression. So when we say the KSP, the solubility product constant, it's just the ions. So, I mean, the solid is included, but it goes away because it's absorbed by the constant, because the solid's concentration is in fact constant. So let's look at this. What is the molar solubility of lead chloride in pure water? So written the hydrolysis reaction here, reaction with water, lead chloride in equilibrium with lead ions and 2 chlorides. So just a plain old initial change equilibrium ice chart. We start off with 0, and I'm going to follow the textbook. I mean, normally we would plus x plus 2x. And what the textbook does is it uses an S, but my S looks like 5, so I usually use a $sign. That's just me. So I can just make sure that it's not a 5 and it's really an S. And so equilibrium then is solubility into solubility. So our KSP is the lead ion times the chloride anion squared. So 1.7 times 10 to the minus 5 equals solubility to solubility squared. And this is the most common mistake. if you're wondering, not squaring the inside. So this equals 4 solubility cubed, or you can 1.7 times 10 to the minus 5 over 4 is solubility cubed, or the cube root is equal to solubility. And what is that? Nope, not Henderson Hasselbalch. Oh, and I'm skipping quite a bit, actually, if you haven't noticed. I'm skipping the whole indicator. Oh, wait. Where's the answer to this one? I guess I could just do the calculations myself. Oh, I can't find it. I'll do the calculations myself. Dangerous concept. All right. Sorry, as you watch me fumble with my calculator. So quantity 1.7 exponent minus 5 divided by 4 to the 1 divided by 3 power. So, ooh, and I can be a Lyft driver too on Maui. Who would have thought? I get ads for my free app. So that means that if you throw lead chloride into pure water, it will dissolve to be 0.0162 molar. And that's not that much, right? I mean, a centimolar, so very, very little. So that's not very, actually, this is one of the more soluble, sparingly soluble salts as well. You can get things really, really insoluble. Okay, so recap for this one. We have a sparingly soluble salt, so lead chloride equilibrium with lead and 2 chlorides. And so we want to know how much will dissolve in water. So we set up our equilibrium, initial change equilibrium. We increase the lead ions by 1 factor of solubility. Think of it as one of the extended reactions. So 1 factor of solubility. Chloride increases by 2 factors of solubility. So our solubility product constant is the lead times the chloride squared. So we put in the solubility for lead, 2 solubilities for chloride. So together that is 4 solubilities cubed. Solve for solubility, we get 0.0162 molar. So questions with this one? All right. So the molar solubility, let's do it backwards. The molar solubility of silver sulfate in water is 1.4 times 10 to the minus 2 molar. What is KSP? So this is one of those where you can't necessarily use the ice chart, but I guess I've been teaching this way, so I'm going to follow through with it. So initial 0, 0, same idea, change plus 2 S, right? Solubility, equilibrium, 2 solubility, solubility. Your KSP is going to be your silver ion squared, sulfate as is, equals 2 solubility squared, solubility equals 4 solubility cubed. But we also know that solubility, we're given the solubility. So 4 times 1.4 times 10 to the minus 2 cubed. And what is that? So 1 point, oh no, wait. minus 2 cubed times 4. How many zeros? 1, 2, 3, 4, 5. Sig fig. So this is going to be 1.1 times 10 to the minus 5. So KSP. So looking at this problem, the previous problem we had solubility product constant, and from that calculated molar solubility. This time we have molar solubility and we calculate solubility product constant. So similar setup, but different answer of sorts. So just going through the process of the ice initial change equilibrium. So, and we set up the same way, but instead of solving for KSP this time, so we write our solubility product constant expression, and similar thing where you get KSP equals 4 solubility cubed. But this time we know solubility, we don't know KSP, so we just put in the solubility and then we get the, then rounding to 2 sig figs, getting the KSP. Questions with this one? So now this is something called the common ion effect. Now, it's bugging me. Where the heck did? Oh, good. Here it is. How did I skip over those pages? I was like, I didn't think the textbook changed. Not that I don't mind putting the numbers in the calculator. So, okay. This is an example of something called the common ion effect. So we have, what is the molar solubility of calcium fluoride in a solution containing 0.1 molar sodium fluoride? So common ion. So what do we have in common? So I don't know. I think of, if I come to class, sorry, I'm going to pick on you, Dennis. Dennis, what do you and I have in common? Well, we're both wearing t-shirts. We both have shoes on. Actually, I don't know if you have shoes on. I'm assuming you do. So we're both wearing t-shirts. We have that in common. So that is something we have in common. What is something that we don't have in common? You are wearing glasses. I am not. So we have things in common and we have things that are not in common. So calcium fluoride has things in common with sodium fluoride. And I hope you don't mind me calling you out. You're like, I'm out of here. No, and so calcium fluoride has things in common with sodium fluoride and has things not in common. What calcium fluoride has in common is the fluoride anion. And then the positive cation they do not have in common. So kind of like that, you have to look and see what's in common, what's not. What's in common though is the fluoride. And what's the difference is the setup here, initial change equilibrium. It's 0 for calcium, but fluoride now, it's 0.1. Because in sodium fluoride, if you remember, all sodium salts are soluble. So 0.1 there. So we're still going to shift right. So we're going to shift right to form the, what do you call it? The sparingly soluble salt. In equilibrium is going to be solubility 0.1 plus 2 solubility. So our KSP is still going to be calcium plus 2, fluoride minus squared. And we know the value of KSP, 1.46 times 10 to the minus 10 equals solubility times the quantity 0.1 plus 2 solubility squared. So this one though, you can apply the variable is small approximation and you can discount because your equilibrium is something to the minus 10, which means it's not really going that far. So the same idea that amount is insignificant compared to the bulk. So you can approximate this as solubility times 0.1 squared. And now the math becomes exceedingly easy. So that means So 0.1 squared is 0.01. You divide those sides by 0.01. This is 1.46 times 10 to the minus 8 is equal to solubility. So did I do that math too fast? No, okay. So of course, you guys have your handy dandy calculators, or if you are good at using Mathematica or MATLAB, go ahead and solve it using your, if you want, go ahead and program your calculator laptop to solve for the variable, to solve for the unknown. It'll, do it like that. It'll do it like that. But if you want to use the old school approximations, you can do it this way as well. So whichever way you prefer. Eventually, though, depends on your major, especially if you're in engineering, you're going to have to do physics and engineering. You're going to have to do, and chemistry, physics, chemistry, engineering, the physical sciences. You'll have to do these approximations in your calculations. So especially even more so in engineering, most of engineering is shortcuts. So, okay, recap for this one. We have, so this is an example of a common ion effect. So now we're looking at solubility of something that's in a common ion. So calcium fluoride dissolved in a solution of sodium fluoride. And if you see then that sodium fluoride, actually it decreases. If you're wondering, does this increase or decrease? This greatly decreases the solubility because of Le Chatelier's principle, right? So Le Chatelier's principle, if you have more reactants or more products, you're going to shift left. It means you're going to have less stuff is going to dissolve. So if you want to keep things from dissolving, a good way to do it is to put it into a counter ion that'll cause it not to dissolve as much. So it dissolves less, but in our equilibrium calculation setup, we have to include the 0.01 molar sodium fluoride anion. So include that in the calculation, and then we can set up the equilibrium expression and then have our one equation, one unknown. And this would be a very difficult problem solving for a cubic. So, but luckily we can get rid of that term, makes the math significantly easier. And then we have the solubility this way. So, but anyone have any questions? So let's.
I have a question.
Go ahead, Kiana.
Sorry, could you review exactly why we are able to get rid of the 2s?
So yeah, this is the variable is small approximation. So what this is saying, do you remember when we talked about magnitude of the size of equilibrium constants? So an equilibrium constant saying 1.46 times 10 to the minus 10, that's saying that it doesn't go very far at all, right? So something to the minus 10. I mean, so what is that? That's 1/10 billionth, right? So I mean, something going forward by a factor of 1/10 billionth, that's really small. I mean, I think a billion is a big number. 10 billion, I'd love to have $10 billion. 1/10 billionth dollar, you're like, well, that's not really worth my effort, right? So 1/10 billionth is not a very big number. And so this reaction is going forward by a factor of 1/10, well, ish 1/10 billionth. So that's very small. And so when you compare the number 0.1, oops, change to a different color. I'll do blue. So that 0.1, when it's looking at an extent of reaction going forward, that's going to be in the factor of a billionth. That's a difference of 10 to the 8th, so ish. And that means that looking at 1/10 billionth versus 0.1, the 0.1 is not going to feel that effect at all. So because of that, you can just kind of say, you know what? poo-poo on you. I'm just gonna ignore that. So it's moving forward so slowly, so insignificantly, you can just ignore it. So you ignore that. And actually, upon ignoring it, what do we get? We get something. I mean, I guess I said 1/10 billionth, and now we're in the 100 millionth range. So, but that's still really small, right? So the reaction goes forward by about a factor of 1/100 millionth, which is very small. And 1/100 millionth is not even close to the same ballpark as 1/10.1. So that means that our assumption is really valid. Does that make sense, Kiana?
Yes, thank you.
Okay. So it's when the variable is small. And for the most part, you can, if you're wondering for this class, when can you and can you not? And I know students always ask this, when can you and when can you not? For this class, when you do sulfuric acid, you have to you can't do the X as small approximation or variable small approximation. And what about real life? It just depends. It depends. If you're designing a space probe that's shooting a bullet at an asteroid, moving at 20 miles a second when you're 300 million miles away, you're probably not going to be able to do an X small approximation. If you are wondering what the pH is of your 3% hydrogen peroxide solution that's been sitting in the closet for 2 months, and you want to make sure your pH is the right value to dye your hair purple for the upcoming, I don't know, Lakers basketball game, then yes, you can use the X small approximation. So it really just depends on what your application is. So I hope that helps. For this class, mostly it works because, I mean, like like pH probes, for instance, I mean, they're awesome, but I mean, like a really amazing, spectacular pH probe could maybe get a pH down to the whatever, a millionth of a thousandth of a pH. And when you're talking about acid dissociation constants that are in like, you know, to the -10, yeah, a pH probe is not going to be able to figure out anything different between that. So I mean, it's very, very useless to include those terms, at least for most chemistry applications. So, other questions? And I know it's uncomfortable, it's weird because you had math, and sorry, I'm going back and philosophizing. You had math and you had these beautiful continuous mathematical model, and then you come to chemistry and we're doing sloppy math. Yes, we are doing sloppy math. It's weird math. We're taking math and we're saying, you know what, we have different variables. Some of them are real, some of them are not. Now we have to figure out which ones are real. And you know what? We don't have to do all these things with math, and we can make our lives easier. And you're like, new rules. So yeah, I know, I understand. Let's see if you can solve this one though. What is the solubility of calcium fluoride in quarter molar calcium nitrate? Okay, you guys are stop writing. How many think it's A? How many think it's B? Okay. So you got some votes for B. I'll spare you the trouble. B is right. Because if you notice, the 2s squared is 4. You can discount that s. And so this is going to be 0.25 times 4 solubility squared. 0.25 times 4 is 1. So KSP is equal to solubility squared, which means solubility is a square root of KSP. So questions with this one? Yeah, go ahead. So what is 0.25 times 4 solubility squared? What is that equal? Yeah. Yep. And you don't need to put 1 in. 1 times something doesn't matter. You can throw away 1. Other questions? Okay, if you follow along in the textbook, you might notice that I've skipped an entire section. I skipped indicators. So part of it is that like, that's really old school technology. No one, this is my own personal philosophy. I think Chem Lab is outdated. I mean, I think right now, robots do all our work, right? I mean, we used to use the Chem Lab is an important thing, but I mean, right now, I mean, it's very few people do Chem Lab. I mean, like, yeah, chemists do, certain biologists do, but if you look at the student population, about 1/4 of all students in college take this class. So it's a huge, it's a fundamental, right? A lot of people take chemistry, and how many of them are actually going to be chemists? And specifically, how many of them are actually going to be chemists that need to know how to do lab stuff? I mean, in a way though, like even I'm a physical chemist. I work with lasers, you know, like, or I used to, at least I used to, I did research with lasers. I mean, the only time I mixed chemicals is when I had to like prepare solutions for my laser. So, I mean, it was, I never would sit there and do titrations or something like that. I'd use a scale and calibrated glassware. That's not even calibrated. I just use a scale to measure out some stuff, and then I would tweak my laser by the light output. So I didn't even have to calculate how much I was doing. So I mean, I understand the Chem Lab is important, but I think it's something that we can, because it's illustrates the skills, but we don't really do it that way anymore. Just like indicators. I mean, indicators is outdated technology. Bearing, you know, us having World War III and knocking us back to the Stone Age, we're not going to need to know how to use indicators. So like I said, I skipped the whole section there because in part of me, I think it's very outdated, and I won't test on it. And in none of the tests, like the American Chemical Society tests or the GRE or the MCAT, or that, none of them have indicators on it. So just so you know. Okay, so next thing we're going to talk about is how you can increase or decrease. Oh, well, I'll talk about how you can decrease solubility. You decrease solubility by adding a common ion. So at the same token, if you can decrease solubility with a common ion, you can increase solubility if you have an ion consumed. And so pH can cause things to become more, and under other circumstances less so soluble. So let me show you an example, this example here. So barium fluoride. And so remember the ions here. So the strong acids. So if you remember, what are the strong acids? Hopefully you've memorized them. HCl, HBr, HI, but not HF. HF is a weak acid. HNO3, H2SO4, HClO4. If you memorize those as strong acids, that means everything else is a weak acid. So including HSO4 minus, this is a weak acid. That's a weak acid as well. So hydrofluoric acid is a weak acid, and bisulfate anion, HSO4 minus, that's a weak acid as well. Everything else is a strong acid. So, which means that the anions, chloride, bromide, iodide, nitrate, bisulfate, perchlorate, these do not react with hydrogen ion, but every other anion will. So everything else will. So let's start with A. So barium fluoride. So barium fluoride is in equilibrium with barium plus 2 plus 2 fluorides. And then what happens when we add H? So add hydrogen ion. What's going to happen? Well, F minus is the conjugate base of HF. HF is a weak acid. Therefore, H plus will consume F minus to form HF. So if it's consuming F minus to form, and this is to form HF, it causes, and then again, another therefore, I guess I have my therefores, I don't know my shorthand logic. Therefore, acid will increase BAF2 solubility. So barium fluoride, as it's reacting, it's going to react until it gets to the KSP, which is barium plus 2 F minus squared. Right, so barium fluoride will continue to dissociate until the combination of the barium plus 2 ion times the fluoride anion squared, until that value reaches the solubility product constant KSP. So it's going to shift right to go that way. As it's shifting right, the fluoride is being consumed. So the fluoride is being consumed, which means it's going to shift right more. That's a very ugly arrow. There we go. There's a better arrow. So hope no one is blue, green, red colorblind, but the fluoride anion concentration is going down because it's being consumed in the acid, which means the reaction has to shift right. As it shifts right, more dissolves. Therefore, dissolving barium fluoride in acid will increase the solubility relative to barium fluoride in pure water. Does that make sense? And how do I know which ion? If it's not one of these, then it's going to react with acid, because these are the counter ions for strong acids. So if it's not a strong acid, it's a weak acid. Luckily, there's only a few strong acids. So fluoride is from HF, it's a weak acid. That means fluoride will be consumed, and then the reaction will shift right. So here's another interesting property about acids, right? They make things more soluble, generally speaking. Does this make sense? You're blinking a little bit. Is it still churning in your brain? Do you have a question? Nope. Okay. All right. let's look at, and students tend to have a hard time with this. Oh, what color should I use? Something, I'll do purple, what the heck. Silver iodide. So silver iodide is in equilibrium with silver ion plus iodide. So iodide, though, is from HI, which is a strong acid. So HI is a strong acid, and therefore iodide does not react. So iodide has no reaction with hydrogen. So with a proton. So iodide is the conjugate base of a strong acid, and the strong acid goes HI one direction, H plus I minus. It does not have the reverse reaction. So hitting iodide with a proton, strong acid, they don't like each other. They're not going to form a compound. So, and well, they might, if you take away the water. If you take away the water, they will form a compound. But in water, hydrogen and iodine, they form hydrogen ion and iodide anion. They don't go the other way at all. Since this time the iodide is not consumed, this one, hydrogen iodide, is not more soluble. So it is not more soluble. It does not react. Make sense? So last one in blue, calcium hydroxide is in equilibrium. Calcium plus 2 OH minus. So of course, if you add hydrogen ion plus hydroxide can react. I guess it's an equilibrium, but it's very far equilibrium to form water. So, but the hydroxide is consumed by by acid, and which means then the hydroxide ion concentration goes down and we shift right. So calcium hydroxide is more soluble in acid relative pure water. So there's another case, calcium hydroxide. So hydroxide reacts with acid to form water. And this is just Le Chatelier's principle. You're looking at the products. So the product, this hydroxide product does react with acid, therefore it decreases. And if you take away a product, you shift right to form more products. And then shifting right means solubility increases. Does that make sense? Yeah, go ahead, please. If you want to think of it that way, that's fine. The way I tend to think of it more is the that it's consumed, therefore you shift right using Le Chatelier's principle. So if you want to say it can't go the other way, I mean that essentially is the same thing, but then you have to include that in equilibrium. So you can think of it that you can think of it as not going backwards. That's equally as valid, but I'm also explaining the way I think. So whichever way works for you. So I remember the previous semester I had students had a really hard time with this, and the example I gave was let's say I was baking cookies for something like the, I don't know, the Alpha Chi Sigma chemistry fraternity event. I had to fill this box of cookies. So, and I had my little sister in the kitchen as I'm making cookies. So as I pull the cookies out of the oven, my little sister would eat the cookies. And if I pulled more out of the oven, she would eat cookies until she was full. And then I could put more cookies in my box. But in order to fill this box full of cookies, I had to satisfy the hunger of my little sister first. So, and the same idea, right? So barium fluoride. So barium fluoride is trying to have its ions be the right amount. So it goes to the KSP, just like filling the box of cookies. It needs to go to this one value. But because there is acid that's consuming, it's consuming one of the products, you have to dissolve more barium fluoride, just like you need to bake more cookies to fill your box to get to your equilibrium. So does that colloquial example make more sense? And so, I mean, and now when you're in the kitchen trying to do that, it's like, let's say that I'm making marshmallow cookies, and marshmallows are made from horses. Like it's a lot of times the collagen is made from horses. I mean, and other animal products. Let's say I have a vegan in the kitchen, and like I'm hungry. I'm a vegan and I'm hungry, but I can't eat those cookies because you got marshmallows. So having a vegan in the kitchen as I'm making marshmallow cookies will not affect. It doesn't matter if I have the someone, because the vegan will not eat the marshmallow cookies. So that's like silver iodide. So iodide does not react with hydrogen, just like a vegan won't eat animal products. Therefore, the presence of silver iodide with someone who has a dietary restriction of a dish you're cooking, doesn't matter if you have an empty kitchen or if you have, a whole army of vegans in there, they're not going to eat your marshmallows, kind of thing. So, whereas if you have chocolate chip cookies, oh, they're gonna gobble those down, right? So it'll go after whatever it is they like to eat, and then you need to make more. So does that make more sense? Maybe, maybe not. Okay. All right. Let's see if you can figure this one out, though. Here's the next one. So I know I've written all over the place. I'll highlight it. So is TSP, trisodium phosphate, is this more soluble in acid? Let me think, yes. Okay, yeah, that's right. And the answer is yes, and the reason why is because this will form 3 sodium and a phosphate. And phosphate is not one of these. Therefore, phosphate will be consumed, and then more trisodium phosphate will dissolve in acid. So the answer is definitely yes. So good, all right, so you get this. Or does anybody have any questions? If not, I will assume that I have so perfectly taught this into your brains that there is no questions. You could ever get anything wrong from this forever and this, whatever, and forevermore. None. Okay, awesome. Score 1 for education. So, all right. So there's a couple of things I want to talk about. So, precipitation formation. So, right, you form an insoluble compound, and you can also have selective precipitation. So this is a very unique way to separate materials. So if you go on and study separation of materials, anybody know what the most common way to separate materials is? Distillation. Distillation is by far the most common way to separate materials. So there are various other ways. You can do something called liquid extraction. So you can, or you can use other methods of extraction. So for instance, you can put cyanide into water and crush up rocks and run it through cyanide to get gold out. You can do the same thing with mercury. So that's more of a liquid solid extraction, but so you can have something that will draw out one of the materials that you want. So, but a less frequently used method is selective precipitation. And you can do this to get to separate out and get in various things of different purity. So for instance, there is a mineral called dolomite. Dolomite is calcium and magnesium hydroxide. So, and dolomite has its uses, but there are some really pure forms of calcium and magnesium that we need. So for instance, so the white computer paper, that uses calcium carbonate, very relatively pure calcium carbonate. And also like Rolaids is relatively pure magnesium hydroxide because it's a drug, right? So we try to keep it to be relatively pure. And so one of the ways you can get this stuff, well, if you take dolomite and you can dissolve it with acid or water, usually something like you can get it, dissolve it, and you can get it into a solution of calcium and magnesium hydroxides. If you add, and so the KSP though, if you look at calcium hydroxide, the KSP is 4 times 10 to the minus 6, and magnesium is 2 times 10 to the minus 13. So it's magnesium is 10 to the 7. It's 10 million times as insoluble. So if you add hydroxide to this solution, you can get rid of the magnesium. So the magnesium will precipitate first. So that's one way you can purify a solution to get rid of one product or another. And why would you want to do this? So one of them is to purify something. Second thing is, say that you want to get rid of a really toxic material. So like chromates, for instance. Chromates are very dangerous. And if you have a little bit of chromate, you can cause a lot of environmental damage. But if you precipitate it out that tiny bit, then it becomes a solid precipitate is much easier to manage than a liquid stream of toxic stuff. So a little tiny bit of precipitate that I can settle down in a tank is much easier than just dumping a little bit of a very toxic material into a waterway. So that's an example where you could use selective precipitation. But you can also, like I said, you can use it to separate out materials that are impure to increase their purity as well. So that's another spin on separation of materials. And then is it the final topic? I forget. Yeah, I guess it's one of the final topics is complex ion. So this is something that we don't cover in this class. It's something called ligand field theory, crystal field theory, and ligand field theory. But briefly, and I've alluded to it a few times. Like for instance, so when we have aluminum ions, the aluminum can form a complex where you have waters and it forms an octahedron. So I've mentioned this before, and actually the aluminum then, this whole thing can I should connect it to the O. And this whole thing becomes a +2 ion, and then a hydrogen ion pops off. So I mentioned this before about how like aluminum, for instance, can actually become an acidic salt. And it's because it reacts with water in this fashion. So similar to water, well, to this. And so really what happens when you have random ions dissolving into the solution, many of them react with water to form complexes. And if you have other things in the solution, they will react with those too. So for instance, silver here, silver already reacts with water. So, I mean, a lot of times we ignore the fact that it reacts with water and we just put the silver ion. But silver does react with water, just like aluminum. But if you put it into an ammonia solution, it forms a complex it'll form this complex with ammonia. And then we have the K formation. So the equilibrium constant of formation, you have products over reactants. You don't include water because it's a liquid. So it's the solvent. So it's not included. So silver ammonia complex times the concentration of silver water complex divided, silver ammonia complex divided by the concentration of the silver water complex times the ammonia concentration squared. And then the formation constant for that is 1.7 times 10 to the 7. So this is a different type of thinking when you do these KFs, these complex ligands when they form, because they're going to form. So like when you're dealing with weak acids and sparingly soluble salts, it almost never happens. So instead of a very small number with a very big number, this goes to the right by a factor of 1.7 times 10 to the 7. So 17 million. So 17 million is a big number. And if you look at some of these numbers. So for instance, silver cyanide. So cyanides are very powerful. You have 10 to the 21. Do they have gold on this? No, they don't. Okay, but you can see here, mercury cyanide, 10 to the 41. So and iron cyanide, 10 to the 35. So cyanides, for instance, they're really, really good at forming complex ions. And this is how we get gold. Okay, so there's a couple ways you can get gold. And so much of gold was made by panning in rivers. I mean, so gold is found in rocks naturally. And if you have a sort of virgin riverbed with the particulates in it, there's probably gold in it. And if you've seen people, you can pan for gold, meaning, and people take like they'll do a sort of a trap of sorts, and they'll run the gold, the silt, and they'll kind of dissolve everything. And if you sit there and you do it over and over and over again, you get gold dust. So that's one way they can get. I mean, it's almost all of the gold dust, though. I mean, we've pretty much captured it all, right? I mean, and then you can mine for gold. You can just look around, see if you find a gold seam. Very frequently silica, so like quartz. If you find rocks that have quartz seams, you take the quartz, if you like pick and hammer and you pick out the gold seam, the quartz seam, and then you pound at it for a while and break all the quartz, you'll get like gold flakes, or gold. You can find gold nuggets in that too. So you can find gold that way, but I mean, let's face it, most of the gold has been taken that way anyways. So there's a couple bad ways to get gold. You can take mud. So you can take water and just like from the riverbed and just run water through it over and over and over again. And you get this heavy mud, and you can pour mercury, like liquid metallic mercury. It's really dense, and you can swish it around in that mud. And then you can take the mercury liquid out, and they do this in the Amazon. So in the Amazon River, and you can take a blowtorch and hit the mercury with a blowtorch. The mercury like volatilizes off, it just boils off, and you're left with this kind of spongy looking gold stuff. It's gold. It's kind of gold, but ends up being kind of spongy. And of course, if you do that, you end up with mercury in the water, and you volatilize, you put mercury in the atmosphere, it settles back down in the water, goes in the system. The people that are doing this, as they're put the blowtorch, they're breathing in the mercury and they're getting neuro damage from it. So it's like, it's bad for everyone. But it's a way that we can get that people illegally get gold. And so another way that we can do it is that we can find rocks that have very low concentrations of gold in them. Same idea, we make heavy mud, we take the rocks, we crunch them up, and we wash them over and over and over again. Then we get this heavy mud. And then after that, you take that heavy mud and you throw cyanide into it. So usually like potassium cyanide or sodium cyanide. And then it'll complex out the metals. So, and it's not just gold. It'll complex out mercury, chromium, silver, but silver is expensive too, so is mercury. So you're probably okay to have that. And then they can take that and you can reduce it. Then you get the cyanide, you take the water from the cyanide, you boil off the water, and then you can reduce the salts, and then you get the metals. So that's the way that we mine for gold now in the United States, because we pretty much have captured all of our easy gold. So, but that's how, like I said, that's how we generate gold now, is by using cyanide. But there are some dangers with that, obviously. So the green way we do it here in the United States, using cyanide, but cyanide, it's not I mean, it smells wonderful. It smells like roasted almonds, but it's kind of dangerous. And the way they do it in the Amazon region, I mean, that's very environmentally unfriendly. So one thing about producing gold in this day and age. But the way we do that, though, is, at least here in the United States, is by the complex ion formation. So let's do a problem with this. So complex ion equilibria. So a 200 milliliter sample solution that's 1.5 times 10⁻³ molar in copper nitrate is mixed with a 250 milliliter sample solution that is 0.2 molar in ammonia. After the solution reaches equilibrium, what is the concentration of copper +2 that originally remains? And the copper +2 probably is complexed with water, but we kind of ignore that for now. So if you're wondering some of these, so the concentrations though, we have a 200 milliliter and a 250 milliliter, and you mix them together. And I've done the setup already for you for that. The initial concentration of copper, because you've diluted it, the initial dilute concentration of copper is 6.7 times 10⁻⁴, and the concentration of ammonia is 0.11. So that's after it's been diluted. So we have copper +2 plus 4 ammonias makes copper ammonia +2 ion. So, and where am I getting these numbers from? Where's copper and ammonia? Copper cyanide. Here we go. So if you look at this chart here, you get this ion here. So copper reacts with ammonia to form copper, ammonia, 4. So it's probably a tetrahedron if it's 4 +2 ion. And then the complex ion formation is 1.7 times 10 to the 13. So big number very far to the right. So That's what we have here. So the KF, I showed you where that's from the chart. So now when you do the initial change equilibrium, so unlike the other ones we've been doing, so the change, I'm saying with this, if you're dealing with 10 to the 13, that's 10 trillion, right? So 10 trillion is a huge number. So, or it's 17 trillion, even bigger. So KF is the number 17 trillion. So that's about the size of our gross domestic product here in the United States. I think it's around $20 trillion, I think. But so that's a big number. 17 trillion is a big number. That means that this reaction pretty much is completely consumed. So the copper is going to be, well, at least the copper water complex is almost entirely consumed. So when we do the change is as if it goes completely away. And then the complex ion is then it just becomes almost entirely, and we're going to have our small value now is how much copper is left over. So a little bit of copper is left over. And 6.7 times 10 to the minus 4, that's a really small number. So you can discount that. You can include in the equilibrium if you want, but you can discount that. It goes pretty much to zero. No, not to zero, it goes pretty much to 0.11. So now equilibrium then, so when we do our KF, so write out our equilibrium, our KF is going to be copper, ammonia, 4 plus 2, concentration, the copper plus 2, I know it's probably water, concentration, NH3 to the 4th power. And we also know this KF value because we showed you before, 1.7 times 10 to the 13 equals, and now we put this from our ice chart, 6.7 times 10 to the minus 4, because the reaction shifts almost all the way to the right. And then we have a really small amount, X, of copper left over, and then ammonia 0.11 to the 4th power. So then we can solve for X. X equals, actually I can just copy it. Maybe I'll just. I like doing math this way, it's fun. So solve for X. So we can pop X out, root. And we can, yeah, I gotta move this over. Move it over that way. Oop, what did we do that for? Go back. And solve for X that way. And what is the value? And in doing so, our X value, throwing in the numbers, we get 2.7 times 10 to the minus 13. Okay, so, all right, so recap for this one. So copper mixing with ammonia to form copper ammonia complex. I want to know how much copper, just aqueous copper, is remaining that has not formed to its complex with ammonia. So when I set up the initial change equilibrium ice chart, so in setting it up, I can say, you know what, the reaction is going to go almost all the way to the right. It's going to be completely consumed. The ammonia, so I can put the extent of reaction pretty much equals the concentration of the copper initially. And that means that the amount of copper complex I'm going to have at the end is pretty much what the original concentration is, because it's a 1-to-1 molar ratio. and I'm left with the equilibrium value very, very close to 0. And I'm going to give this one our unknown number. And I'm being very careful with my words, because usually previously when I would give the unknown usually was the extent of a reaction. This time we're assuming the extent of a reaction is pretty much all the way to the right, and then we're only left with a very small amount of whatever reactant that we have left over. So then we, by using this logic, then write the formation equilibrium value and then put in the numbers here. The numbers, the KF value is 17 trillion equals 0.00067 divided by the quantity, or divided by x times 0.11 to the 4th power. Then we solve for x and we get x equals 2.7 times 10 to the minus 13. So it means it's going to be molar. So very, very small amounts. So do you see the logic in this? So I think I have like one problem on this. If this is too hard for you, this is something you can skip. I mean, I do have a single problem on this, but I mean, if it hurts your brain too much, stick to the other type. But you might see this in the future with inorganic chem. So I do have to teach this. So questions? All right, last concept. Amphoteric metal hydroxide. So amphoteric means things that act like acids and bases. So aluminum hydroxide. Aluminum hydroxide is an example of that. So aluminum hydroxide, if you react it with acid, the acid will consume the hydroxide. And aluminum hydroxide also reacts with the base to form an aluminum hydroxide complex. So that's an interesting thing about hydroxides. Hydroxides, they can also act like bases, so the metal, like them together. So this is not necessarily something I'm going to test you on, but this is just something that's kind of cool. That's like how certain things, depending on their environment, can be amphoteric. So, and I mentioned before, the most common amphoteric substances are water and amino acids. Amino acids are amphoteric, but their amino acids are amphoteric depending on their environment. So they're not as versatile as water. Water is very amphoteric, but metal hydroxides, depending on their environments, they can be amphoteric as well. So just kind of cool how chemistry has all these weird rules. I know it, and I think it's really cool. That chemistry does that, but I know a lot of other people are like, too many rules. But this is fun, at least for me. So if you can peer into my mind. So I think I'm done for chapter 18, and I do have a little bit of extra time. I'm trying to think. Do you guys? And Dennis, I remember you wanted to have a problem. You said last class where you have looked at the buffer and how it changes with response to the environment with the acids or bases. I know there are some problems I can do in that. I'm just thinking about class on Monday or Wednesday. I can do a problem session where I do a bunch of problems for you. Do you guys want a problem session, or would you rather go through the material and have more time at the end of the semester? What are you guys feeling? Yeah. Fair enough. Yeah, that's more the end of the semester then. Yeah. Well, the nice thing is, like, the material is going to get easier. At least, well, we get to the Nernst equation, 2 chapters, and that's kind of hard. But I mean, like, the kinetics is tough, right? So you come into class, you have the natural logs you have to deal with, and you have to deal with kinetics, which is like all calculus. And then you have equilibrium and acids and bases, which is pretty complex. And when you get to this chapter, the equilibrium, it's actually getting easier. And next chapter is thermo, which is highly conceptual with some numbers in there. It gets even easier. Electrochem, maybe a little harder, but it's still not as hard as the other stuff. And then nuclear chem at this level is almost all conceptual. So actually nuclear chemistry is easier than chemistry, much easier. So although a bit more difficult and dangerous to deal with. But so yeah, we're on the upswing. So unlike, I don't know how many other classes like at the end is really tough. We're getting easier. Organic 2 is like that too. When you take organic 2, it gets easier near the end. It gets tough. Organic 1, you get tough near the end with NMR and stuff. But anyways, all right, well, I'll look at the schedule and I'll let you guys know if anything changes as far as like presentation stuff. But all right, class is over. Any last minute question or stuff? Okay. All right, then I will stop there. Kiana, you say something or you just?
Thank you.
Oh, you're welcome.